előadásában. So Kim, welcome you on board again. I think we can start, and feel free to start whenever you are ready. The floor is yours.
Perfect. Thanks very much, and I'm ready. So my name is Gunn Maver. I'm the chief geologist here at GreenTherma. So I'm dialing in from Copenhagen in Denmark. That's where we have our headquarters. So what I'd like to present to you today is a new closed-loop geothermal solution that is really ideal for district heating. So delivering heat to district heating without the use of heat pumps. So really a very efficient solution. And the basic concept here is the concept you see here on the right-hand side, where we drill down 3 to 5 kilometers vertically down to 150 degrees, and then we have a horizontal part to the well. And inside this closed system, we will flow water, and we can deliver that directly into a district heating network. My background is I have a PhD in geology from University of Copenhagen, and I have a business degree as well. I worked about 35 years in the oil and gas industry, and then I was one of the founders of GreenTherma about 3.5 years ago. As I said before, we are based here in Copenhagen in Denmark, but we are setting up an office in Hamburg as well. We have a presence in Houston, and we also have a development office in Stavanger. One of my colleagues is from Hungary, so Laszlo. So he's been so kind to actually translate all these slides into Hungarian. And if required, please feel free to distribute them among yourselves. And you here see the headquarters where I'm sitting right now down doing this call. Maybe a few words just on geothermal heat to start with. So just some fun facts. So 90% of the Earth is actually more than 1,000 degrees hot, and 99.9% is more than 100 degrees hot. So in many ways, you can say it's amazing we could stand here on the surface. But this is the heat that we really want to utilize. And the heat, it really comes from the creation of the Earth and from radioactive decay. The belief is the Earth will last is about 4.5 billion years old, and it will last another 7-8 billion years. So again, there's heat, more than enough for everyone. On average, because we want to extract heat, if we look around the globe, if you are on land, the temperature will increase with about 30 degrees per kilometer. In Hungary, you're actually very fortunate because it actually increases faster. And that means we don't have to drill so deep to get the same amount of energy out. And again, drilling is an expensive part of this kind of project. And I think you're already familiar with geothermal heat. This is a picture I just found from Budapest. So this is the heat we want to extract, but by going much deeper, we can go up to 100, 150 degrees. So we can deliver heat directly to a district heating network. You're probably familiar with geothermal. It's, as I said, it's already been used in Hungary, but also in other countries. So it's quite common in Munich, for example, in Paris. It's been implemented in Copenhagen as well. So the classical way of doing this is drilling down 2 to 3 kilometers into a highly porous permeable layer. And then what you would do is you would inject cold water, typically your return water from district heating, and it will flow through the underground in these specific layers. And then you have another well where you pump up the water that's now been heated up. And then you circulate it out to, for example, your district heating plant. If this solution works, it's very efficient, but it's not very many places where you can really get it to work, because it has a lot of requirements of the subsurface. It has to have a certain porosity permeability, which is very difficult to find. You have a lot of problems with things to get up in this well over here, because you are sort of flowing water through the subsurface, so you're cleaning out the subsurface, so you get a lot of corrosion. You need downhole pumps in both of the wells to actually circulate the water. You can't go so deep you can only go down to 2-3 kilometers because you have to have a porosity in the subsurface to flow the water. So in general, the water you get up is not very hot, so you need heat pumps on the surface. So to try and overcome or mitigate all these issues, we have developed a closed loop solution that you see here on the right-hand side. So what we will do is we'll drill down 3 to 5 kilometers and then have horizontal section to the well. The well is completely encased, so there's no water flowing between the well and the geology. So this is really like a radiator. Inside this outer pipe you see here, that's enclosed, we put another pipe for the full length of the well, but that's open out here at the end. The idea is, again, we take the return water from your district heating network, flow it down, and then here essentially especially along the horizontal section, it heats up, initial to 150 degrees, goes into the inner pipe and flows to the surface. Because it's so hot, we don't need a heat pump, we just need a heat exchanger, and you circulate the water to your end customer. A problem with this type of solution is that you lose a lot of the heat, because this is a long well and you have cold water down, hot water coming up. So our invention is that the inner pipe here is not one pipe, but 2 pipes. And this space you see here, that's a vacuum. So essentially what we've done is put a long thermal flask into the well. So instead of losing 30-40% of your energy on the way back, you only lose a few percent. And the other trick we've done here is adding a long horizontal section, so the water have more time to travel along the hot section. This type of well can look complicated, but 70-80% of all wells onshore US for oil and gas are drilled exactly like this. So here there's no maintenance, there's no downhole equipment, it's all just a small surface container. So here you see some of the pipe dimensions. The dimensions of the pipes and type of pipes are standard oil and gas type pipes. So we can buy them off the shelf anywhere in the world. Again, there's no downhole equipment along here. The only thing we have is a small surface container that I'll show you in a minute that has a vacuum pump, so we can actually maintain the vacuum if we lose it over time in the pipe, a small circulation pump, an expansion tank, and monitoring board, and that's it. So the maintenance is all done on the surface. And here you clearly see, if we take a cross section of this pipe, this is the outer pipe. You have the geology out here. The blue is then the cold water flowing down. The red is the hot water coming up. And the inner pipe here is 2 pipes. And then this white space here is the thermal flask or the vacuum. And that is continuous all the way to the end of the well. So if for some reason we lose the vacuum over time, we have a vacuum pump up here, and we can easily recreate the vacuum. So we believe this system can last 50 to 100 years. If you treat your district heating pipes the right way, and we use the same type of fluid, it's been proven in many places they have a lifetime of way above 50 years. So essentially, these are the pipes we're using. These are the 2 inner pipes, and this space you see here, that is where we have the vacuum. Each pipe, 2 pipes together, comes in 10-meter section, and then they are slowly lowered down into the wellbore. On the surface, the only thing we need is this 20-foot container with a little bit of equipment. And that equipment, that's what is listed here on the left-hand side. So again, circulation pump, a vacuum pump, expansion tank, heat exchanger, and a monitoring board. So very easy to maintain. And if you want to put this below ground, below a parking lot, that's definitely possible as well. Each well can actually produce around 2 megawatts of heat, depending a little bit on the temperature you need on the surface. So if we want to do more than 1 well, we will do them in a pattern like you see here, where we drill down, the wells will be 6 meters apart, and then we come down at a certain depth. They will then go out in a star pattern. And we can easily do 5 or 10 wells from 1 well site. And that way we can come up with a project, 5 wells, 10 megawatt. And remember, this is continuous production. You should expect a downtime of less than 1% a year. So this is 10 megawatts full load all the time, 24/7. So this is the basic concept we are proposing. So we have a small surface container here with all our equipment. We drill down 4 or 5 kilometers, horizontal well, similar distance, so 8-9 kilometer long well. We flow up the water. So you come from your district heating network, you deliver the 60 degrees or 50 degrees. We flow that down, comes up, and we can then deliver 100 degrees on the surface. If you want either higher or lower temperature on the surface delivered to you, we can do that as well. And we control that by changing the flow rate in the pipes. So the faster we flow, the colder the water will get. The main requirement here is that the temperature down here at depth needs to be somewhat higher than the temperature that you need in your pipes, because we will cool the subsurface and there will be a small heat loss. If you just think about geothermal, looking concept of other renewable energies. So if you look at the capacity of solar, that operates maybe 20% of the time, wind 85 or 45% of the time. Of course, it depends on time of year and exactly where you are. And geothermal, you would say more than 90%. But you saw that small surface facility and the limited equipment we have. So we think it will operate at least 99% of the time, year after year. And it can do that for 50 to 100 years. If you look at the surface footprint, so another thing that's a concern for people, how much do it sees in the landscape. So certainly here in Denmark, there's a lot of discussions about these solar panels and also windmills. We have them all over the place. People are not very happy. There you can see the megawatt produced per square meter. Geothermal is by far the smallest of any of the renewable energies. So you get very reliable energy from the subsurface, but the surface footprint is also really minimal. So any intervention, this is a very, very secure way of producing heat. As I said earlier, we are a fairly young company, so we are through a development process. So in 2024, we took this vacuumized pipe and installed it in a well, an oil and gas test well onshore Stavanger. We could see that the vacuum actually holds and the insulation effect is as we expected. So we only lose a few % of the energy on the way back to the surface. Then late last year, we started repurposing an existing well, a hydrothermal well, north of Berlin in Germany. That's this well you see here. So it goes down to about 4 kilometers. So and it's open down here because they have already tried to circulate water from this well to this well as a hydrothermal solution. It did not work. So we put a plug down here because we need a closed system. And then this month we will start installing 3.2 kilometers of our pipes inside here. And this will be a test facility for us for at least the next 1 year. Then our first real well to be drilled, that will be drilled the end of this year in Denmark. So we've got a grant from the Danish government for 11.5 million euros to drill this well, which is 4.5 kilometers deep and 2.5 kilometers horizontal. So again, this shape you see here. We have a heat offtake agreement with the local utility company, Aalborg. It's about a city of about 120,000 people. They will take all the heat we can produce for the next 30 years. And what's interesting here is that they will pay twice as much for the heat in the wintertime as they will in the summertime. So things that we are working on is actually changing the flow rate in the well. So we produce slightly more heat in the wintertime and slightly less heat in the summertime. If you produce less heat in the summertime, the subsurface will partially reheat, so you can actually extract more heat during the wintertime. So then we can actually adjust some of the fluctuations that you would have in your district heating demand. And then what we are looking at right now is what we would say a multi-well project. So where we produce 10 megawatts of heat, and it will probably be for district heating. Our key markets to look at right now, because that's very favorable geology, is Denmark, Netherlands, Germany, Poland, Hungary, Switzerland, and Austria. So as part of this process, we've been around presenting this concept. And again, it's all places well received. People are in general very familiar with hydrothermal solutions and understand all the issues and concern there's with hydrothermal solution. So they see this as a very attractive alternative. So we are talking with one district heating company in Denmark where we have a signed LOI, so letter of intent interest. And also talking with a lot of German cities, so Hamburg, Flensburg, Wismar, and Kaiserslautern. So for each of these cities, we will go in and we will review their subsurface, all the data that they have available. We will get access to the heat demand. So what's your base load, your peak load, what's your forward and return temperature? Which locations could you imagine to do geothermal in your city? And all that we put together in a study, and then we come up with a model to say how much could we actually produce, what would be the levelized cost of heat, and how could this be financed, and who could be partners in a project like this. And again, if any of you are interested in doing the same kind of exercise, we would be very keen to engage with you. So a nice thing about Hungary is that you have an oil and gas industry. So a lot of the data we need to map the subsurface is found in connection with the oil and gas industry. So it's drilling deep wells, which you have a lot of, and it's also acquisition of seismic data. So seismic data, for those of you who don't know what that is really like a brain scan. So it's an image of the subsurface of the geology. That means we can actually plan our well and optimize the well path. And what you see here in red, that's all the hydrocarbon fields, oil and gas fields you have in Hungary. So all these locations, I know there'll be a lot of data that we could potentially review. So one of the things that's very important is that we want a high temperature. So the higher temperature in the subsurface, the less kilometers we need to drill. So on this map, you have an outline of Hungary, and this is the temperature you will find at a roughly 2.5 kilometers. On average in Europe, the temperature is about 30 degrees per kilometer. But you see here, for example, there's areas where the temperature goes all the way up to 150 degrees. So that means for 150 degrees at 2.5 kilometers, that will be around 60 degrees per kilometer in gradient. So here, down in this area, in this whole corridor, we only need to drill down 2.5, 3 kilometers to really reach our the temperature we need for our facility. Whereas in this region here, we need to drill slightly deeper. But on average, this temperature gradient you have with depth in Hungary is one of the best in Europe. So in my mind, for this type of solution I'm proposing, Hungary is one of the hotspots. The other thing we need to look at is how deep can we drill before we get into very hard rocks. So like basement rocks, so granites, for example. So if you look at the Alps, that type of rocks. So because of your temperature, we want to be able to drill 2.5, 3 kilometers at a minimum. And here you have the depths to the basement. So again, in this area here, for example, you see that we could drill 7, 8 kilometers before we hit anything hard. So it's only maybe in this area here where the hard rocks are very, very shallow, and down here where they're very shallow, it could be more costly to drill. But otherwise, in large part of Hungary, we can drill very deep and you have a very high temperature gradient, which is just perfect for the solution that I'm proposing. And you can match that with the temperature map we looked at here before, because we got to combine those. So you see we have very high temperatures in this region, and we have a large depth down to where the rock gets very hard. So ideal drilling conditions and ideal for producing geothermal heat. So this is my final slide, just to round off, just to summarize. So this is a closed loops horizontal geothermal well solution. It mitigates all the issues you see with a hydrothermal solution, where you have to drill at least 2 wells and pump water from one well to the other. The idea is that you have a district heating network. We take your return water, 60 degrees. It could be slightly lower, it could be slightly higher. We flow that down our closed loop solution, and then especially along the horizontal section, the water will heat to the temperature of the subsurface. It will then return in our thermal flask, so the insulated pipe, go here to the surface. In here in this facility, we'll have a small heat exchanger, and you can then send the water directly out to your end customer. And with that, thanks very much for your time and attention. I'm really impressed with the number of people that signed up. You see my email address here, so please do write to me if there's anything you want to discuss, and I'm happy to come down and visit you in Hungary as well.
Thank you very much for this insightful presentation. It was a pleasure for us to hear about your technology.
Thank you.
A közönséghez fordulnék, hogy van-e valakinek kérdése az előadóhoz.
And if there's any questions, I'm happy. I think we have plenty of time, so you can either write them in the chat or just fire away.
Nyugodtan lehet a chatbe is küldeni, ha valaki szeretne.
So I see there's one question here on the chat. So the 11.5 million euros for the Danish well, that covers about 65% of the total well cost. So the total well cost is around 18 million euros. And that well would produce about 1.4 megawatts. But what you have to remember here, this is a one-off well, so there's a lot of one-time cost, mob, demob of rig, seismic acquisition. We have universities involved. So we think on a longer scale, this type of well should be drilled for around 10, 12 million euros. That's our plan. And again, that's why we would like to propose we drill not just one well at a location, but 4 or 5 wells at the same time. That will really bring down the cost. And there's also a question from Istvan about how much we are delivering to the local city. And it's for them, it's also a development project. So it's a fraction of the city's total demand. What we would normally recommend is that we are part of your base load, not your peak load, because this needs to run all the time because the investment upfront is so high. So if you have a peak load of let's say 100 megawatts, you probably have a base load around 10, 15 megawatts. So in that case, we would suggest 6, 7 wells from one well site. Any other questions?
All right, I can't see any more questions, so they can reach out to you in your email, right?
Yes. If you want, I can just bring it up again. So it's kgm@greentherma.com. And I have some publications I can send. I have some marketing material. So whatever you need, I will be happy to share with you. And if we need to do it maybe both in English and Hungarian, I can have my Hungarian colleague Laszlo. He could join a Teams call for more in-depth discussion and presentation.
Perfect. Okay, so thank you again very much for your presentation. I think that's it for today. Hope to keep in touch with you. That's all.
Likewise.
Bye-bye. Köszönjük szépen mindenkinek a figyelmet. A fenti e-mail címen további kérdésekkel el lehet érni az előadót, és további szép napot kívánok mindenkinek.